So in this tutorial lecture, we will discuss some use of differential forms and exterior calculus to complement what we have discussed in the main lecture. So we will reformulate the vector calculus in R3 in terms of differential form. Let's begin. So in R3, we'll work with the Cartesian coordinates. So we have 3 coordinates, and which will denote by x, y, and z. So now we know the zero form, nothing but a scalar, right? So let's write it down. Zero form, scale phi of x. In general, it's just a number and there is no basis associated with it. Remember, if d is the space-time dimension, for example, here is 3, then the number of bases associated with a p form is d choose p. So for zero form, it is 3 choose 0, which is just 1, and this is nothing but just a scalar. In general, its component or this will be the single element which will be a function of coordinate x, a scalar field in general. Now, what about the one form? So the number of basis elements for one form is 3 choose 1, which is 3. So the basis elements are dx, dy, and dz, the coordinate differential. And a generic one form in this basis denoted by p this sub 1, which have this component. Right. In general, these components are functions of the space-time coordinates. In this case, on the spatial coordinate, that is x, y, and z. So now the two forms in this language, and the number of basis elements for them is again 3. You can count it. So 3 is the dimension of the space, 2 is the two form, rank of form is 3. And what are the elements? Dx, wage, dy, wage, dz, we have set a ordering of the form that will have x, y, z in this order. X, y. Okay. And a generic two form can be written this way. Here, note that we have written this component in a slightly unusual way compared to what we discussed in the class. Why we have done that? Because we can identify these components then as a component of a 3 vector. But 3 vector in this three-dimensional Euclidean space. We have a component denoted by omega 1, 2, 3, and here we can identify omega 1, 2, but we have discussed in the class as 2 times omega 3 and so. Okay, this is just to make contact with the vector calculus R3. Finally, 3 form will be spanned by only 3 by 3, one basis element. We know that the elementary volume in the three-dimensional Euclidean space is d3x, which is nothing but dx wage dy wage dz, and a generic 3 form written as some function of coordinate x, d3x. Remember, x vector is nothing but x, y, and so one can easily see that these 1 form, 2 form, 3 forms are basis elements are also respectively the line area and the volume element. So you can check by checking how they transforms under coordinate. You have to find the Jacobian, and then you can verify this statement. Now consider various wedge product. Now let us consider a wedge product of a 1 form U with another 1 form V. So let's do it. So U1 dx U2 dy plus U3 dz is wedge with the V1, again, which we can write in terms of component and basis, dy plus dz. Now let's do this explicitly. So remember that this is a antisymmetric product. So dx wedge dx will be 0 only when this element from here is not the same element from this second line, then the corresponding wedge product will be non-manageable. So keeping in mind, we'll have, let's say you have this term, it will have wedge with this term, we give u1 v2 with dx wedge dy. But remember that dx wedge dy is equal to minus of dy wedge dx. So if you take this term and this term, it will give you u2 times v1 and dy wedge dx, which you can write as minus dx wedge. So you will get the following: u2 v1 dx wedge dy, and you have u2 v3 minus u3 v2 with dy wedge dz plus u3 v1 minus u1 v3 dx, dz dx. And if you carefully look about these combinations, these are nothing but components of a cross product of u and v. So you can rewrite it as u1 wedge v1 epsilon ijk in u cross. V k component the basis of dxi dx. Remember that if you write u1 as a 3-component vector with u1, u2, u3 as a component and v as 3-component vector, v1, v2, v3, you construct the cross product, and that will have that matrix will have these elements. Then you can rewrite it in this nice form. This is the 3-dimensional Lebesgue data, which is totally antisymmetric in IJK. Also, let's do an wedge product between V, 1 form, and a 2 form, omega 2. Again, let's write it down. V in terms of basis and component, y, dz, and this will be wedge with omega 1 in dy dz plus omega 2 dz dx plus omega 3 dx. So we have basically used this notation for that is okay. Now let's do this product, and we will see that only vanishing contributions are d1 omega 1, this term with this term will give dx wedge dy wedge dz. Right. Again, this term, if you try to wedge it, because it will have dy wedge dy wedge dz, but this is antisymmetric. If 2 elements are same, it's 0. We have only 3 vanishing term from here. So v1 w1 into w2 3, and then dx1. Yeah, this is of course makes sense because this is a 1 form, this is a 2 form, and their wedge part will give a 3 form. Similarly, the example before, we have this is 1 form and this is 1 form, their wedge part is giving a 2, which is written in terms of this wedge basis of 2 covariant differential. Now, if you look at it and think that this is a component of a 3 vectors, this v1, v2, v3, and similarly this is a component of another 3 vector, omega 1, omega 2, omega 3. This is nothing but dot product, and can write it as e1 dot w1 omega, or and we know that dx wedge dy wedge dz is just the elementary volume. Right. Now let's look at the Hodge operation. So if we take Hodge dual of 1, what is that? Remember the definition of Hodge dual? It will be, so 1 is like a 0 form, so it will convert it to a d minus p form. So p is 0 and d is 3, so 3 form. Okay. So this is the 3 factorial, this is d minus p factorial. It's 3p 0, so 3 factorial, and there is some epsilon 3 index ijk. You have dxi dxj ijk takes 1, 2, 3 value xyz, and this is nothing but dx wedge dy wedge dz this d3. So weight star of one is basically the elementary volume element. Okay. Now, what about the star or the Hodge dual of it? It will be, it is one form. The star of this will give a two form. The dual form is the two form. Again, d minus p, so 3 minus 1 to factorial. Then there will be epsilon, but this one index up and two index corresponding to two form lower. And then dx square wedge dx. So what this gives? Let's write it down component by component. So star of dx is nothing but dy dz star of dy dz dx and star of dz is equal to dx wedge dy. Just plug in the various components and keep in mind that epsilon IUK is totally antisymmetric. You will have this. Now, what about Hodge dual of that is star of dxi dx. Now, this is a two form. Taking a star of that, you are working in 3 dimension, so it will give you a one form. So again, d minus p 3. This will be a 2 factorial ij k and dx. Okay, so let's write it in component by component. So sorry, one typo. This should be d minus p. So d is 3, p is this 2 form. Factorial will not be there. So d minus p is 1 factorial. Okay, the component form. This is dx star of nothing but dz star of dy dz is equal to dx star of dy, sorry, dz dx equal to dy. Now from this, one can also show that star of a 3 form of this thing, dx wedge dy wedge dz, nothing but 1. What you have to do is that take star both sides, right? So take a star of this, and this side you have dx wedge dy wedge dz, and you get back 1. Remember, we discussed star of a form in the class. You can use that same form. Now we can use this and now take star of both sides. Okay. If you take star both sides, then what we should get? Let's do that. We will take also the star of this one and see what we should get. Now star of one wedge E1 is nothing but right. This is two form, and star will give you a one form component of constitute a component of a vector in 3 dimension in this case, and we know that this is a 3 vector in R3, like cross product of 2 vector. Similarly, E wedge form gives you the dot product, which is expected because this is already a 3 form, so wedge will give a 0 form, and this is exactly that scalar. Okay. Now armed with this, let us write down the various elements of the vector calculus in terms of the language of exterior derivative and stuff. Let's see how to do that. Easiest thing is that take the exterior derivative d of a scalar phi. So now by definition, this is delta I phi. So it gives a exterior derivative makes a p form to p plus 1 form. So phi is a 0 form, so it keeps a 1 form. And there was no other index to antisymmetry, so we just have del I phi dxi. And in the vector calculus notation, usual, this is nothing but this del phi dot dx, right? So what is this? Now you should be able to identify what is this. The d phi. This is del of phi is nothing but the gradient of the phi, and it is giving the how this phi changing. Then let's take the one form E1, take a D. So we can again write it down explicitly. Remember the definition of D. One form V1, you can write it as a Bi dxi in the component, so one index. So D will give you a partial del J. So in the component form, Pi you should write as Pi dxi, and then you take D, this is J, and the wedge product basis. So now write it component by component, and you will see that you get the form. 2 V1 y plus 3v2 minus 3v2 dy wedge dz, and then del 3v1 minus del 1v3 insert wedge dx. And you can identify that again, you can write this as epsilon ijk times the curl of va and the kth component of that, right, in the basis of dxi wedge dx. D of this v1 is nothing but epsilon ijk curl of v component again. Just to remind you that repeated indices are summed over, and here ijk just take 1, 2, 3 value, and these are all special indices, so we don't have to bother about the opposite sign that is associated with the time coordinate, because we are just working in R3. So essentially, the position of the index up down, it becomes a little bit trivial, because it doesn't, while you are raising and lowering, there's no negative sign change. Essentially, the metric is just a Kronecker delta ij with +1 +1 +1 at the time. Now, if we do a straight derivative of a 2 form, that should give a 3 form. Of this form, and then this is nothing but the del dot omega. This is nothing, it's giving you a divergence, right? So now if you take the star of both sides of these two things, star of the A1, star dot dx, and star of 2. So we have rewritten curl of a vector, divergence of a vector in terms of star and d acting on 1 form and 2 form respectively. Okay. So we have almost recasted everything that you learned in your vector calculus in R3 in terms of the star and d, and this constitute the exterior calculus. Now you can see the connections. So one more thing is that we know that d square 0 could apply to any form, right? So now let's apply to a 0 form. D square phi is 0. Phi is a 0 form. Let's take a star of it, and this should be 0. So now what this is given? This side we have star, we have d, and then another d of taken phi. But right, we have written the d of phi 0 form is nothing but a gradient of phi dot dx. Okay. Now if you take d of this is now you are taking a d of a 1 form and then taking a star. So what is happening? So let's remind, take d of 1 form and then you take a star, which gives you the curl of that. Right? So if you do that, this is like a 1 form, then you take a d star, that will give you a curl of this nabla phi. It's nothing but and this implies that curl of a gradient of a phi scalar is 0. So this is one of the famous vector calculus identity that you have encountered, which follows from acting d square on a 0 form. Now if you do the same exercise and act d square on a 1 form, again 0, and then take star, by definition 0. So you can see that this will give, please do that algebra. Del dot e. This is another famous vector identity that you have encountered in vector calculus in R3. The curl of a vector, then take a divergence of that is 0. So one thing just to remind you, when you are taking this derivative, you have to uh, insert this Levici beta, and then further you are taking a star, then there will be another Levici beta, and index of which will be contracted with this index of Levici beta. So just to remind you, suppose you have two Levici beta whose two of the indices are contracted, then it will give you a delta on this rest of the two indices with a 2 factorial. We have used that actually. And also, if you have contracted all three indices, this will just give you 1. It should be well known from your vector calculus. One needs to use this again and again, many contexts. It's just to remind you that this kind of manipulation we have done. Okay. Now, what about the Laplacian del square? Can you write it down in terms of this d star and these kind of things? The answer is yes, and we leave that for you to think how to write it down. Think about the Laplacian, you might think that this is very symmetric, and these d and star, these act on some antisymmetric tensors, but you can found a combination of them such that it gives the Laplacian operator. Think about how to do that. So before we end, let's discuss one more thing. So let's consider again this Minkowski spacetime. Go back to R3, 1, and let's assume that there is a one form whose component satisfy this. Okay. Then you can able to show that if you take d of that, then take a star, and then take d, then take again a star. This will give you minus del alpha omega. Now this is nothing but the D'Alembert in 3 plus 1 space-time dimension. And if this condition holds, then you can show them. It's just an algebra. You should take d of these and then take star d and then star that. But based on what we are discussing in the lecture and in the beginning of this tutorial, you should be able to do that. And just give a hint how to do that. So d of omega is basically del nu omega mu dx nu d wedge dx nu. Okay, and then you have to take a star of it, right? How to take a, then if you take star of these star d omega, schematically there will be some epsilon. So already it has become this is a one form, so this becomes a two form. Star of it will give you a d minus t form. So d is now 4, so it gives another 2 form. It will be of form something like right, something like this. Delta mu rho sigma, and then you have to take d and star again, but that will give you another epsilon. And note that if you have epsilon, or rather 2 epsilon, let's say one is this index alpha beta, another epsilon co-index mu1 mu2 rho sigma. So 2 of these indices are contracted, And of course, you can raise and lower the indices by your Minkowski matrix tensor. Note that this field has to be antisymmetric in alpha, beta, and rho sigma as well, the resulting object. And you can show that this is nothing but delta beta sigma minus. So you can see that if you interchange rho sigma, this is antisymmetric. Interchange alpha beta, it is antisymmetric. And there's a 2 of the indices are contracted. There will be a 2 factor. So you have to use this, and then you will get this relation if this condition satisfies. So you can see that if this condition satisfies, this gives you nothing but the D'Alembert, and we'll see that this negative signs makes this operator positive. We'll end here and hope that you will now be able to do manipulation with the differential form easily. Thank you for this.